Hi everybody, Marty Geyer here from your gsp295 class, and we're back in week 3 and to talk about an exciting topic, recursion. Now recursion is a very conceptually difficult topic. It's kind of one of those things that is similar to a lot of advanced math. If you've ever had a problem, I know I have, taking a lot of advanced math, but not being the most brilliant mathematician in the world. Sometimes you're drudging along with a problem and you're just confused, you don't get anywhere, and then suddenly it clicks, right? That's kind of what recursion is like in some instances. So it's a very tough conceptual topic, and I highly encourage you to get a lot of practice, look at a lot of examples, listen to this lecture, and I hope all these help you get that click going faster. Recursion is very powerful and very fun to do, so I don't want you to be discouraged by it. So let's start with a very simple example of factorial here. So factorial is just from your book, takes an integer n, and it has a base case and a recursive case. And let's kind of run through this first, and I'll explain more. So in the case where n equals 0, then if n equals 0, return 1. And we just return 1 to the caller, and now the factorial of 1 is 1. Now, so that's a very simple case. Let's take the case of 2. So if we take 2 and go in here, I'm sorry, let's skip 1. Let's take 1 first. If we take 1, if n equals 0, which it does not, and so we skip that return. Otherwise, return 1 times the factorial of 0. Factorial of 0 we just did, that goes in, back in here, and you get n equals 0, return 1. So I've written it here, sorry. So return 1 times the factorial of 0. Factorial of 0 goes back in separately and says, if n equals 0, return 1. So we put 1 there, and now we get 1 times 1, which is 1, and that's returned. Now it's very important to have that return. I've seen a couple students skip that just because they're in a hurry or they're forgetting this conceptually. Because remember what happens if you don't have the return, you'll still compute this calculation. So you still call a recursive function, and it still will be a recursive function, but what will happen is you never return that value, and there's an implicit return 0 at the end of a function if you don't return a value, you'll recall. So you'll end up with return 0, which is not the right result at all when you expected to return some complex number here based on the recursion. So when you're doing the recursion, remember to actually return the results of the recursion. That's a very common mistake. So you can see, now let's take like 3. If you do 3, then 3 does not equal 0, so we skip that. So return 3 times factorial of 2. And let's see, let's put that there. So 3 times factorial of 2. And you go back in here, this skips again, return 2 times factorial of 1, which is what I have written here. And now factorial of 1 goes back in, you get 0, and now n equals 0, return 1. And so we get 1 there, and then the 1 that was from that multiplication of factorial of 2. So 1 times the factorial of 0 there, which is right here, which is just 1, and that comes out here. And then 2, which was that initial number we were taking in there, and then 3, and you get 6. It's a very quick trace, so I know that probably is not completely clear. I encourage you to kind of do this on your own. But you can convince yourself by running these examples and tracing through the code. You kind of put each number down or make a whole instance of the code like the book does to trace through it. There's a couple important points here. There's base case and a recursive case to every problem. Now, base case is basically a point at which the answer is immediately obvious to you. So when you're planning something or when you're doing complex addition, let's say, you might not be able to add 672 plus 456 immediately in your head like that, right? So that's not a base case. That would be a recursive case. But when you break down the addition to a simple addition, like 1 plus 4, 5, boom, done, easy. That's a basic case. So the basic case is the point at which the problem can't get any smaller, or rather, not that it can't get any smaller, but it's immediately obvious what the answer is, and you can just return it. The recursive case is always breaking down the problem into a smaller piece. So recursive case is where you have you always have a reduction, like in this case where you have n minus 1. If we took this out and we just made it n, for example, we'd infinitely recurse. because you pass in n here, and it simply calls itself n times, and it always does that. It never reduces the problem. Always keeps going. So that's bad. If you took out the base case, also you would just spin infinitely, because when you get to, you took this out, when you get to 0, that's not done, and you just go to -1, -2, -3, and you keep going infinitely. That's really a big problem with recursion, is if you mess up, your code will run infinitely. That's pretty much the standard what happens when you mess up with recursion. And that's a pretty big bad thing to happen. You don't really want that to happen, especially in corporate code or building a game or anything like that. You can't have the game just completely crash and freeze up and spin forever on you. Worse than that, not only would it crash the program, but it might chew up resources on the computer itself and crash the computer, and that's even worse. So the consequences to recursion are bad. I don't want that to scare you too much, but enough to think that you have to get this right and think this through. A quick word about the runtimes of recursion. So big O usually isn't different just because you've made a function into recursion. So factorial is a great example here. This is O of n, because you're still doing this over n numbers. So if we plug in 10 here, we do 10 times 9 times 8 times 7 times 6. You're still doing the basic same calculation in the same way. So if we change this and made it a for loop, like you might think to do with a normal factorial without recursion, it's still O of n. So you haven't changed the runtime. Now, you have changed the space time a little bit, because recursion, basically, you'll read through this in the book, I'm not going to go into the detail here, is it creates a new stack instance. So you have to create new memory for all the variables in here, and you have to do that each time you recurse. So when you recurse a lot of times, you chew up a significant amount of memory. I don't want to quantify that with saying how much, because it really depends on the problem, and it really isn't that much compared to the massive amounts of memory we have in computing these days, which is why we don't worry about it most of the time. And I won't say don't do recursion because it chews up memory. That's usually not something you hear. But you should be aware that it does chew up some memory, some additional memory. And if there's a very large problem, that could be an issue. So you do need to be aware of it. But it's usually not a showstopper. And the runtime is usually the same. So there's no, I've seen students make that mistake before where they're thinking, well, it's got to be slower to do it this way. No, it really isn't. And big O runtimes, it's really the same thing. But sometimes it can be different depending on how you've programmed it still, of course. As we've seen, you can have two different algorithms that perform the same function, do very different things. So you still have to be careful of that. So let's go through Fibonacci real quick, and first of all, I'll go through that to explain why this is actually a bad example of recursion. Because here you have two recursive cases, return Fibonacci n-1, n-2. These two recursive, actually I'm getting ahead of myself, so I'm going to leave that for you for an exercise because there isn't enough time to explain it. But you should go through Fibonacci and do some web research or run through it and convince yourself that this is actually doing repetitive work that you could do a little better if you didn't write it in this particular way. So if you created a loop and did something slightly different, you can create a O of n runtime function. This is actually much worse than an O of n runtime function here. So recursion can come back to bite you if you're not careful, and it's sometimes very difficult because you can't immediately stare at this and translate it into an big O type function. You have to think it through and think through the process of actually what it's doing, and then you can convert. So there's some confusion there. But Fibonacci here is an example of a more complex recursion where you actually have two base cases. And this can happen, so you should be aware this is a good example case of it, where Fibonacci of 0, pass in 0, you return 0. If you pass in a negative number, you return 0. If you pass in 1, then that's also a base case, you return 1. But now if you pass in 2, if you go Fibonacci of 2, Fibonacci of 2 will skip these cases, go down here, return Fibonacci of 1 plus Fibonacci of 0. Fibonacci of 1 Fibonacci of 1 goes back in here and returns 1. Fibonacci of 0 goes back in here and returns 0. And so you get 0 plus 1 is 1. It's Fibonacci 2. And Fibonacci 3 will come in here and compute Fibonacci 2 and Fibonacci 1. Fibonacci 1 again is 1. Fibonacci 2 we just did is 1. And you get 1 plus 1 is 2. And you can run through these examples, and you should, to give yourself lots of good cases. So I hope this has been slightly helpful to run through everything. Please let me know if you have any questions, and I hope you enjoy this week's lab. I created it myself, and it's kind of a fun playing with recursion and sorting. Take it easy.